Welcome to the Ultimate Physics channel. In this video, we are going to solve some problems on relativistic Doppler effect. Relativistic Doppler effect is the effect in which light of a certain frequency gets altered due to the relative motion between the source of the light and the observer. The Doppler effect in sound is non-relativistic as sound waves require a material medium for propagation, and hence the absolute motion of either the source or the observer or both matter there. But in the case of Doppler effect in light waves can travel in vacuum. And since only relative motion between the source and the observer matter here, this Doppler effect is called as the relativistic Doppler effect. Now we need to know certain expressions for Doppler effect in order to solve some problems on this topic. For those of you who are not familiar with the concept of relativistic Doppler effect, we have posted a couple of lecture videos on this topic in this channel. So I would suggest that you please go and check out those videos before you try to solve these problems here. Let us check the expressions for Doppler effect. So if an observer is in a frame of reference S and if he is measuring the wavelength or frequency of light source, he will measure either a higher or lower wavelength or frequency of light waves due to the relative motion between the source of light and the observer himself. The general expressions for frequency and wavelength of light waves in relativistic Doppler effect in light waves are respectively given by f is equal to f naught square root of 1 plus or minus beta over 1 minus or plus beta. This is for the frequency of the observed wave due to Doppler effect, and the wavelength lambda is given by lambda naught square root of 1 plus or minus beta over 1 minus or plus beta. Here it is important to remember that for any wave, if the frequency increases, its wavelength has to decrease if the wave travels with a constant velocity in a medium, which is true for the light waves as well. So here in these expressions, f naught and lambda naught are the actual frequency and wavelength of the source, and f and lambda are the observed frequency and wavelength respectively. We know that beta is the ratio between the relative velocity between the source and the observer at the speed of light, that is c. So beta is equal to u over c. Now the plus or the minus sign, when do we use these signs? The plus sign in the numerator is applicable when the source and the observer are approaching each other for the frequency. And if there is plus sign in the numerator, the denominator obviously has to become negative sign in front of beta. So it is 1 plus beta over 1 minus beta within the square root multiplied by f naught will be f when the source and the observer approach each other. When we have taken frequency with that expression, the wavelength correspondingly will be opposite of it. So it will be lambda is equal to lambda naught times square root of 1 minus beta over 1 plus beta within the square root. Similarly, for frequency expression, the numerator within the square root will have a minus sign and the denominator plus sign if the source and the observer recede away from each other. When we've taken that expression for frequency, corresponding wavelength expression would have opposite signs on the numerator and the denominator, that is lambda is equal to lambda naught square root of 1 plus beta over 1 minus beta. So I will put out the expression separately here. I've just combined all of these 4 different cases here and given us 2 simple expressions. Now corresponding time periods between the light signals can also be calculated using this formula. T is equal to T naught square root of 1 minus plus u over c. Instead of beta here I have used u over c over 1 plus u over c. So this is again the reverse of the time period expressions, inverse of that. Now with these ideas in mind, we can proceed to solve some problems on this topic. Let us do the first problem here. Sometime in the distant future, an astronaut in space runs red light. Red light of wavelength lambda is equal to 650 nanometers. While speeding in his spaceship, as it appears green, that is lambda is equal to 540 nanometers to him. What is his speed? So we can imagine that in the distant future, space traffic uh, is regulated with the traffic signals. So an astronaut traveling in such a spaceship uh, kind of is observing some light signal position somewhere in space, and it is a red signal basically from the source of 650 nanometers wavelength. Lambda is equal to 650, but the astronaut who is sitting inside, because of the velocity of his spaceship with respect to the signal, thinks that that is lambda is equal to only 540, and he assumes that that is green, and he runs red light. Now if this is the case, what would have been his speed? That is the question. So it's very simple relativistic Doppler effect question. We can directly use lambda expressions for this. Lambda is equal to lambda naught. Here, since red appears to be green, we take the spectrum, the electromagnetic spectrum, and particularly the visible part of it, violet, indigo, blue, green, yellow, orange, and red. We can clearly see that red has shifted towards this side because red appears to him as green. That means this is blue shifting. Red has a maximum wavelength, violet has a minimum wavelength. It is shifting towards a lower wavelength here in this case for him. So it is basically called as the blue shifting of the light waves. Here, since blue shifting has occurred, that means he is approaching the wavelength has decreased, right? So that means he is approaching the source of light. That is the meaning we can easily have. So for this case, the formula would be lambda is equal to lambda naught square root of 1 minus beta over 1 plus beta, where our beta is u over c. We need to find out u here, right? What is the speed? That is our u, relative velocity between the spaceship and the signal, light signal, right? That's the other thing. So we have the lambda as 540, which is green, 540 nanometers, and lambda naught is the actual wavelength of the source, that is 650 nanometers, right? So we can get the beta by doing a reverse of this, right? So square root of 1 minus beta over 1 plus beta is equal to lambda is 540 over lambda naught is 650, and then we can do this expression directly. 540 over 650 is 0.831, let's say. So go to the next page. Square roots we have to do. So 1 plus beta, 1 minus beta, if I'm right? Sorry, 1 minus and plus, sorry. So 1 minus beta over 1 plus beta is equal to, so I've squared here on both sides, that is 0.690. So 1 minus beta is equal to 0.690 minus 0.690 beta. Sorry, denominator is plus sign, so we have this. Now if I take things to the other side, this is 1 minus 0.690. That would be equal to 1.690 beta. Therefore, beta would be equal to 0.3098, or yeah, so 310 we can take 1.690 beta. Sorry, not beta, just 1.690. This would be equal to 1.81833. So the speed is 0.183 c. This is the speed with which he is going, so that the signal appears to him as the red signal appears to him as a blue signal, right? So this is the speed with which he has to move. Right, let's proceed to the next problem. How fast must one be moving for red light of wavelength 650 nanometers to appear? Yellow of wavelength lambda is equal to 590 nanometers, and blue of wavelength 460 nanometers, right? So how fast must he be moving? Right, here we have two cases. Let's deal with the first case, that is yellow light. Lambda is equal to 590 nanometers. Now red of 650 has blue shifted to 590 yellow. So again, it is blue shifting formula. So in this case, we have to use again the same original formula, that is lambda is getting shifted to lambda naught. That means the wavelength has reduced. So it is a square root of 1 minus beta over 1 plus beta. So lambda by lambda naught is 590 nanometers yellow over 650 here, which is square root of 1 minus beta over 1 plus beta, and that would be 0.908 is square root of 1 minus beta over 1 plus beta. Or if you square on both sides, you have 0.824 is 1 minus beta over 1 plus beta. So that would be 0.824 plus 0.824 beta on the left side would be equal to 1 minus beta, or 1.824 beta is equal to 1 minus 0.824, or beta would be equal to 0.176 over 1.824. That would be 0.0965, or beta is equal to 0.097. So the speed must be in the first case 0.097 c. Right, because it is blue shifting, we have to use this expression with a minus sign on the numerator. Right, Let's go to the next case here, that is a B case where it is 460. So here I have to substitute 460 in this thing here in the numerator here and work out. So here again, same thing, it is also again blue shifting. Sorry. So if I proceed to do that here, my B section would be 460 nanometers over 650. That is further blue shifted down to blue color directly from red. The first case it is yellow, from red to yellow. Here it is from red to blue. So more blue shifting here occurs. So here again the same thing, 1 minus beta, 1 plus beta. So if I work out, I get U is equal to, in the second case, about 0.333C. So I suggest that you could pause the video for each of these problems and attempt the solutions on your own, and then you can cross verify with the solutions that we provide here. Right, let's move on to the next one. A distant galaxy is moving away at a speed of U is equal to 1.85 into 10 power 7 meters per second with respect to Earth. Calculate the fractional redshift of light from this galaxy. So this terminology, fractional redshift, is nothing but it refers to our equation. For example, we have an equation, let's say lambda is equal to lambda naught square root of, this is fractional redshift. A galaxy, we know that most distant galaxies move away from the Earth. So in this case, it is fractional redshifting of the wavelength occurs. That means the galaxy is moving away from us. So it is lambda is equal to lambda naught. Wavelength increases, so it is 1 plus beta, 1 minus beta. This is the expression that we have to use here. So if I use that expression, I would get, if I subtract lambda naught on both sides, right? I would say lambda is minus lambda naught on the left side. Right side also I would have lambda naught square root of 1 plus beta over 1 minus beta minus lambda naught. If I take lambda naught out commonly, on the left side if I bring it, I would say it is lambda over lambda minus lambda naught over lambda naught. That would be my square root of 1 plus beta over 1 minus beta minus 1, because there is a lambda naught that has been taken out commonly. Now this particular quantity is my fractional redshift, right, on the left side. So the quantity that I have on the left side is fractional redshift. So whenever there is a mention of fractional redshift, you have to remember that it is not the actual redshift, is what percentage of the original wavelength is getting redshifted, so to say, a fraction of it, right? So we have to calculate the speed of the galaxy in this particular case. So the speed has been given, here, so we have to calculate the fractional redshift, that is lambda is equal to lambda minus lambda naught over lambda naught. That is what we have to directly calculate. So U over C, if we calculate here, it is 1.85 into 10 power 7 over C is 3 into 10 power 8. So U over C, if you work out, this turns out to be beta, which is equal to 0.0617. Okay. Now we have 1 plus beta over 1 minus beta, the whole thing. So the right hand side, if I work out here, that would be square root of 1 plus 0.0617 over 1 minus 0.0617 minus 1. And this whole thing turns out to be 0.0637, and that is our fractional redshifting. So this is the answer in this case. Right. Let's move to the next one. Light from a nearby star is getting blue shifted by about 2%. Is the star approaching us or is it receding away? What is the speed relative to us? So here this is blue shifting, that is, it is shifting towards lower wavelength. So when a star is approaching us on Earth, its frequency will increase. That means in terms of wavelength, we can say that from red it is getting blue shifted towards lower wavelength. For that to occur, if the wavelength is getting smaller, that means the star must be approaching us, right? The wavelength, smaller space for the waves to move, so it is getting compressed, so to say. You can remember that way, right? So please do check out our videos on Doppler effect. 2 lecture videos have been posted on relativistic Doppler effect, and if you don't get how we are getting this blue shifting, red shifting, this thing, you probably have to check that video to understand this, right? So what is its speed? That is a question now. So we have a point here, 2% shifting. That means we can directly write the observed frequency f must be 1.02 f naught, the actual frequency, because it is 2%. I'm adding that 0.02 to 1. So that would be my observed frequency, because it is getting blue shifted in terms of wavelength. That means the frequency has to increase, that is by 2%. Increase is given here, right? So that directly we can see that this particular portion, if we compare this with our original formula for blue shifting of frequencies, it is 1 plus beta, 1 minus beta with an f naught here. So from here we can easily get beta. So I do this math here, f over f naught, right? F is 1.02, so we can directly do beta here also, right? So we just have to take the square root and write it as 1 plus beta over 1 minus beta is 1.02 by comparing these two equations. Therefore, if I square out on both sides, the right hand side I get 1.0404, whereas on the left side I have 1 plus beta over 1 minus beta, because I have squared on both sides. So if I retain 1 plus beta on this side, I have 1.0404 minus 1.0404 beta on the right side. So if I rearrange the terms, I get beta to be equal to 0.0404 over 1.0404. So I continue here, my beta would be equal to 0.0198. This is my beta. That for the speed here is u is equal to 0.0198 c. Beta is u over c. So if you want it in terms of absolute speed, that would be u is equal to 0.059 into 10 power 8 meters per second. This is the answer to that question, right? Let's move on to the next one. Yeah, the wavelength of red light in stellar spectrum due to emission from atomic hydrogen is typically around 653.3 nanometers. Lambda is equal to 656.3 nanometers, which corresponds to the H alpha spectral line of the hydrogen atom, that is H alpha spectral line. Compute the wavelength of that light observed at Earth from three stars receding directly from us with relative speeds 10 power minus 3, 10 power minus 2 and 10 power minus 1. So we have three different cases here. Let's do it. First case, u is equal to 10 power minus 3c. That means u over c is 10 power minus 3. Here the stars are receding directly from us, so we have to use lambda is equal to, the wavelengths are going to, therefore if the stars are receding away from us, the frequency is increasing, so wavelength has to decrease. Receding away from us, frequency decreasing, wavelength has to increase. So wavelength increases means we have this formula 1 plus beta, 1 minus beta here, right? So lambda is equal to, in all the three cases we have to use this formula now, right? So lambda is equal to lambda naught, which is 656.3 nanometers, and multiply that by square root of 1 plus u over c is 10 power minus 3, which is beta, denominator 1 minus 10 power minus 3. So that would be equal to 656.3 times square root of 1.001 10 power minus 3, right? So it is 0.999, right? That would be, if you do the math, 656.96 nanometers. So the original 656.3 goes to 656.96 nanometers. That is an increase in 0.66 nanometers in wavelength. So that is clearly redshifting, because wavelength is increasing towards the larger side. So it is a redshifting of the wavelength. So as the star recedes away from us. The second is 10 power minus 2c case, where u is 10 power minus 2c. So yeah, right? So we have beta as u over c, which is 10 power minus 2 in this case. So same procedure we have to repeat. So lambda is equal to 656.3 times square root of 1 plus 10 power minus 2 over 1 minus 10 power minus 2. So if you do the math here, because of the higher velocity, obviously we will have more redshifting. So this is going to go to 662.9, so to say, nanometers. So this is further increased, right? The third case is 10 power minus 1c, that is about 10% of the speed of light, right? So beta is 10 power minus 1. Therefore, the lambda is equal to 656.31 plus 10 power minus 1 over 1 minus 10 power minus 1. That is 656.3 square root of 1 point, in this case 1 over 0.9. So if you do the math, lambda will turn out to be 725.6, let's say, nanometers. So it's further increased towards, so 725.6 indicates that it is going to the infrared region, right? It's larger than the visible red light. So it's infrared region, completely redshifted, right? So these are the three values you got to be getting in this one, right? So let's move to the next one. That's the sixth problem. The signal sent from a spacecraft has a frequency of 1400 Hertz. What is the frequency of this signal as measured on Earth if the spacecraft is receding from us at about 0.95 C? So here the actual frequency is given as 1400 Hertz. So that is, let's say, F naught in our case. We write F naught, that is 1400 Hertz. Right. So what is F? That is the question here. From a spacecraft, and this is receding from us, so we have to use the formula. F is equal to F naught, the frequency has to reduce, so it is 1 minus beta over 1 plus beta. And here it is 0.95 C. U is given here, right? U is equal to 0.95 C. So U over C is 0.95. That means our beta in this formula is directly 0.95 we can use. So here F is equal to 1400 hertz. I mean, it should be kilohertz, right? It's a kilohertz, 1400 kilohertz. Or hertz also doesn't matter anyway, right? So it is 1400 kilohertz, square root of 1 plus 0.95 by 1, oh sorry, 1 minus in the numerator and 1 plus in the denominator, right? The frequency has to reduce if it is receding from us. So the denominator should have a plus sign, the numerator should have a minus sign, right? So if you do the math, 1400 into 10 power 3 here, kilohertz, 1 minus 0.95, 1 plus 0.95, turns out to be frequency 220 kilohertz. To do the math there. That's the answer to this question. Right, the next one, the acceleration of a spaceship moving radially away from Earth is 29.4 meters per second squared. Sodium vapor street lamps, right, on Earth emit light of wavelength lambda is equal to 589 nanometers. How much time will it take for the astronauts on the spaceship using a powerful telescope for the sodium street lamps to become invisible? So clearly, we know that it is sodium vapor lamps emit typically yellow spectrum, yellow color light, right? Light of yellow color, whose wavelength is 589 nanometers. So for this yellow to become invisible, lambda goes to what color then? That is completely redshift, right? Invisible it becomes. That means in our spectrum, visible spectrum, the corner beyond yellow in this direction becomes invisible. So here it is clearly moving away, it is given. That means the wavelength has to increase towards red and then to infrared. Typically, even if it goes to infrared, we can assume that it is becoming invisible. So typically there is no mention of what wavelength it goes to, just it is becoming invisible. If it is becoming invisible, in such cases, we have to take some safe value, right? Because 650 is typically red, 650 to 700 is hazy, 700 I can safely assume to be IR. So let's say I say that IR, where my lambda naught is 589 nanometers, it goes to lambda, which is, let us say, 700 nanometers. Here it is a completely assumption that I am doing, because it has to become safely invisible to me. I can't see 700 nanometers, right? So, right. Now the question here is, how much time it will take for this to happen if the speeding spaceship that is moving readily away from the Earth should not see any, even with a powerful microscope, any light emitted by one of our street lamps having a sodium vapor source emitting at 589 nanometers. That is the question, right? So in this case, I can start with simple equations, try to get this thing, because we know that the formula for this one, the equation, Doppler effect equation, we know that is, in this case specifically, lambda is equal to lambda naught square root of 1 plus beta 1 minus beta, because it is receding away from us and wavelength is increasing, so it has to be plus on the numerator and minus in the denominator. Right. So we need to get we are given acceleration rather than the velocity here, so we have to use that and try to work this out. Right, so we can say that let us start writing some equations for this. Velocity I have acceleration, so I straight away write v squared is equal to u squared plus 2as. I take initially the velocity of the spaceship when it started from Earth to be initial velocity u at 0 in this case. So the velocity of the spaceship can be written using this equation as 2as within the square root. Here I don't know the distance, so I can again do another equation for that, right? Which is the distance that the spaceship travels in a time is half ut plus half at squared, right? Right. So here initially u is 0, so my s is just half at squared. So my t is square root of 2s over a. I know the acceleration, I don't know the distance, so I'm trying to work it out. So instead of s, I can substitute either directly this also. So I don't even need this. I can substitute directly s here, this formula, plug this s here, and I have a already, so I can just put the s here and then I get v. So if I do that, v is equal to square root of 2a times half ad squared, which is my s. So if I cancel these two out, I get a squared, t squared as v. So v is obviously a very straightforward 80, right? Now I can use this one to get the lambda, right? So my lambda is safely shifting to 700. So lambda is equal to lambda naught times square root of 1 plus beta. 1 minus beta is the original expression. Here I take lambda to be 700, and here it is 589 nanometers for lambda naught. Square root of 1 plus beta over 1 minus beta. So 700 over 589 would be my term in the square root, 1 plus beta, 1 minus beta. And I can directly write 700 over 589 is equal to square root of 1 plus, my beta is u over c, or v over c, whatever it is. Here we have taken v, right? V is equal to 80, so it is 80 over c over 1 minus 80 over c. So if I square on both sides and do this value, I get 1 plus 80 over c over 1 minus 80 over c is equal to 1.412. This is the evaluation of this 700 over 589, and then squaring it. So 700 over 589 and then squaring it, right? That would be this. So if I rearrange these terms, 1 plus 80 over c on the left side is 1.412 into 1 minus 80 over c on the right side. And then if I separate the terms out, I get 2.412 80 over c on one side, and right side I get 0.412. Therefore, if I do 80 over c, I get 0.171. I know acceleration is 29.4 meters per second squared. So I need time alone t. So t is equal to 0.171 times c over a. So if I do that, I'm getting t as 1.74 times 10 power 6 seconds in seconds. So it is roughly about 20 days, 20.14 days. So that is the time it would take for a speeding spaceship accelerating at 29.4 meters per second square to not observe uh, a light from a sodium vapor lamp, street lamp of 589 nanometers on Earth to become, of course, invisible, right? That was our original question. We have answered that. Okay, let's move on to the next problem. A physics professor conducts an exam to her students aboard a spaceship that travels at 0.5 c. The duration of the exam is 2 hours on the spaceship. She stays on Earth during the exam and signals the start of the exam just as the spaceship passes by her. How much Earth time should she wait before she can signal the end of the exam? The problem here is about Doppler effect affecting the signals, right? Any signal that is sent between traveling observers in relative motion, those signals get affected because of Doppler effect. And in the introduction of the video, we have given the formula for this, where the frequency is getting affected as well as the time period because of that. So it is t here is a time period between two signals is equal to t naught times square root of 1 minus beta, I write, over 1 plus beta. Why do I take minus sign here? Typically, the time between two signals has to reduce if in this particular situation, because uh, the students are going to return back to Earth after the exam's over. So I assume that here they are approaching Earth on the return part of the journey when the professor would be signaling the end of the exam. Because initially she starts the exam with a signal, that is her first signal, and then when the students are returning after the completion of the exam, they must be approaching Earth. So in that case, they are approaching, so she's sending her second signal to indicate the stop, to stop the exam. And those signals have to take lesser and lesser time to reach them because it is approaching. They are approaching the Earth. So I have to use a minus sign in the numerator here and a plus sign in the denominator for the approaching phase. That is why here we have to use this. Right. Here the speed of the spaceship is given as 0.5 c as it recedes or approaches us. So it is u over c is 0.5 c, or u over c is 0.5, or that's beta is 0.5. U is 0.5 c. So I can directly substitute these values in this formula. T is equal to T naught is 2 hours. So 2 times square root of 1 minus 0.5 over 1 plus 0.5. T is equal to 2 over square root of 0.5 over 1.5, or 1 over 3 square root. So T is equal to 2 times 0.577 years. The unit here is, sorry, hours, right? Example, right? So T is equal to 1.155 hours. So on Earth, the professor has to just wait for about 1.155 hours before she says the exam is over. So please indicate that with the signal so that on the spaceship it will have been 2 hours for the students, they will have completed the exam. That's the answer to this question. Let's move on to the next one. A spacecraft transmits data back to Earth at the rate of 1 into 10 power 4 pulses per second. What is the rate at which these pulses are received on Earth if the spacecraft is speeding at 0.97 c with respect to the Earth? So it is receding here, right? Transmits data back to the Earth. So rate of reception of the signal. At what rate this is received on Earth? So I use F is equal to F naught times square root of 1 minus beta over 1 plus beta. This is for the receding formula, right? Receding away from Earth. So F is equal to, signals are 10 power 4 pulses per S, that is my frequency, so 10 power 4. And I need beta, or U rather, right? No, it is given as 0.97C. Beta is given as 0.97 here. So I can substitute that 10 power 4 square root of 1 minus 0.97 over 1 plus 0.97. So I have to get F here. Therefore, my frequency F is equal to 10 power 4 into this one whole thing. To work out, it will be 0.1234. Therefore, the frequency in this case is 1.234 if you want into 10 power 3 hertz or pulses per second. Right. So that is reducing to a lower value because the spacecraft is receding from Earth, right? Yeah. So let's move on to the next one. The frequencies of spectral lines from a distant galaxy are 2/3 as high as the frequencies of the same spectral lines from nearby stars. So here the comparison of the spectral lines is between the nearby stars to the distant galaxies. Distant galaxies, we know, are typically receding away from us, whereas nearby stars are approaching us. So comparing these two frequencies, what would be the speed of recession of these distant galaxies? Obviously, the Doppler shift formula for frequency here in this case is recession frequency. So it is F is equal to F naught square root of 1 minus beta over 1 plus beta. Because for receding galaxies, distant galaxies, the frequency has to reduce. Here F is given as 2/3 of F naught. Actual frequency F naught, 2/3 of that is our observed frequency F. So if I compare these two formula, directly I can write my square root of 1 minus beta over 1 plus beta is 2 over 3. So if I do the square on both sides, I say 1 minus beta over 1 plus beta is 4 over 9. 1 minus beta is 4 over 9 times 1 plus beta. 9 minus 9 beta is 4 plus 4 beta. And therefore my beta would be 13 beta would be 5. So beta would be 5 over 13. So your U over C is 5 over 13. That gives me U is equal to 0.385C. This is the speed with which these distant galaxies are receding away from the Earth. Okay, so that completes the problems that we wanted to solve, some of the problems that we wanted to solve on the topic of relativistic Doppler effect. So I always suggest that please attempt the problems on your own before watching the solution, and lecture videos have been posted on this topic. So you could probably go back and check those lecture videos before attempting to solve these problems in these problem videos. Thanks for watching.